Okay, I did 3 exercises. Let me take the PDF and let's see how I did those exercises. So I did 1.11. Yes, a function f is defined by the rule that the function returns n if n is less than 3, and otherwise returns this f of n minus 1 plus 2f of n minus 2 plus 3f of n minus 3. And exercise asks to write a procedure that computes f by means of a recursive process. And also to write a procedure that computes f by means of an iterative process. So let's take the code. Give me 1 second. Let me find the screen, the right window. Code. Where is code? Here. Okay. Now I have to find the window with the code. Yes. Here we go. So, writing the procedure for the recursive process is very simple because you just need to define this function that takes an argument n, and then you have a conditional procedure. As you can see, if n is less than 3, the procedure returns n, otherwise the procedure calls itself in a recursive fashion. This is very simple. As we saw in the book, in this case, the time complexity is exponential, and we have a lot of redundant operations, and the space instead grows linearly with n. Instead, the iterative process is a bit more complex to understand and also to visualize. I had to write it first in Python because I still need to get used to the prefix notation, which is still very confusing and makes and is giving me a hard time to write proper code and also to visualize what I'm writing. I need to get used to that notation, to that syntax. But I mean, it's just 3 or 4 days that I'm coding this scheme, so I think it's totally fine, totally okay. So let's see the iterative process written in Python. We have a stopping condition. If n is less than 3, then return n. Otherwise, we have we define these variables. A is equal to 0, B is equal to 1, C is equal to 2, and then we have a loop construct that counts from 2 to n, which is in practice n minus 1 because range, the range function in Python works in this way. And inside this loop, we can compute the next value, which is c plus 2b plus 3a. And then we can substitute swap the values in the variables, and a takes the value of b, b takes the value of c, and c takes the value of next value. And finally, at the end of the loop, we can return c. So at this point, it should be enough clear how to proceed, and we only have to translate this in scheme using the prefix notation. So we define this fi that stands for function iter, and inside this definition, we have another definition. We have a nested definition of iter. Iter takes 4 arguments, a, b, c, which are the values that need to be updated, and count, that counts how many loops we have to do. We have immediately a stopping condition, so that when count is equal to n, we can return c. Otherwise, we can call in an iterative fashion the function iter. And we call the function iter passing the arguments b, c, and the sum of c, 2b, and 3a. That, as you can see, is exactly what we were doing before in Python. And of course, we pass also the count incremented by 1. Then, in the body of the main definition, so in the definition of fi, we have a stopping condition, so that if n is equal 3, we return, if n is less than 3, we return n. Otherwise, we call iter with the same initial values of the arguments as we saw in the Python example, so 0, 1, 2, and 2, which is the count argument. So in this case, the meaning of the variable is that a represents f of n minus 2, b represents f of n minus 1, and c represents f of n. So more precisely, during the iteration, a is equal count minus 2, b represents count minus 1, and c represents f of count. So when count is equal to 2, we start with a equal to 0, b equal to 1, and c equal to 2. And then the next value is f of count plus 1, which is exactly c plus 2b plus 3a. And in this case, as we saw in the book, the time complexity grows linearly with n, and instead the space complexity is constant, OD1. And as told many times in the book, the recursive version has a recursive process because it expands into a tree of deferred computations. And instead, the iterative version has a recursive procedure, but an iterative process, because the entire state of the computation is carried explicitly in the parameters. And by using this time, we can also measure the time that is necessary to run to execute this function. And it's important to use time. You have to import this base package. So you can find this code on my GitHub, and you can try it yourself. Let's go on. Let's go on. So, exercise 1.15. Let's take the text. Let's take the test. Okay. The text of the exercise 1.15 reads: the sine of an angle specified in radians can be computed by making use of the approximation sen of x, approximately is x, if x is sufficiently small, and the trigonometric identity sen x is equal to 3 multiplied by sen of x divided by 3 minus 4 sen cube of x divided by 3 to reduce the size of the argument of sin. For purposes of this exercise, an angle is considered sufficiently small if its magnitude is not greater than 0.1 radians. These ideas are incorporated in the following procedures, and the questions are: how many times is the procedure P applied when sine of 12.15 is evaluated? And the second question is: what is the order of growth in space and number of steps, so complexity of time and space, as a function of A used by the process generated by the sine procedure when sine of A is evaluated? So let's see, here we have this definition, the definition of cube, the definition of P, and the definition of sine. Here I defined also pi, just to make some attempts and to compute the sine of 12.15. But it's enough to reason a bit about the problem. I mean, P is applied once for every time sine has to divide the angle by 3. Before the angle becomes small enough, that is, before the absolute value of the angle is less or equal 0.1, which is the number we are given by the text of the exercise. So for sine of 12.15, we have the following divisions. We have a first division that gives us 4.05, then another one, and we have 1.35, another one, and we have 0.45, another one, and we have 0.15, and another one, and we finally have 0.05, which is less than 0.1, and in this case the recursion stops. So basically the recursive calls look like this, and P, as you can see, is applied 5 times. So the first question is answered, and the answer is P. And instead, the other one that was asking about the the space and time complexity as a function of A. Also in this case, we need to reason a bit about the problem, and we know that each recursive step divides the angle by 3. So we have A divided by 3, A divided by 9, A divided by 27, and we know that the process stops when A divided by 3 to the power of n is less or equal 0.1. So we just need to rearrange this equation, and we have that 3 to the power of n has to be greater than 10 multiplied by the absolute value of A, and that is n must be greater than greater or equal to the logarithm in base 3 of 10 multiplied by the absolute value of A. So we can say that the number of recursive steps, so the time complexity, grows logarithmically in A. And we also know that each level does a constant amount of work, one division, one test, and one application of P. So the procedure P itself does constant work, and so the number of steps, we know that number of steps is grows logarithmically with A, and the same we can say for the space complexity. And also we have to consider another note that I wrote here, because the process is recursive, not iterative. We must acknowledge that there are pending operations like P that calls P applied to P, applied to P, applied to P on the stack until the base case is reached. Well, we can pass to the final exercise for this video, which is the 1.17. Let's look at the text. The exponentiation algorithms in this section are based on performing exponentiation by means of repeated multiplication. In a similar way, one can perform integer multiplication by means of repeated addition. So basically, one can, I want to stress because it is the entire point of the exercise. One can perform integer multiplication by means of repeated addition. The following multiplication procedure, in which it is assumed that our language can only add and not multiply, is analogous to the ext procedure that we have seen before. This algorithm takes a number of steps that is linear in B. Now, suppose we include, together with addition, operations double, which doubles an integer, and halve, which divides an even integer by 2. Using this, design a multiplication procedure analogous to fast exp that uses a logarithmic number of steps. Okay. So we have the definition given by the book, where we redefine the multiplication of two integers. We have the stopping condition. When b is equal to 0, we return 0. Otherwise, we call in a recursive fashion the function star itself. Here I reported the text of the exercise. I started with the definition of double. Of course, I don't use the star, the multiplication sign, and I use the addition. And I also defined even, which returns true if the remainder of the division of x by 2 is 0, and otherwise returns false. Then I defined half that takes one argument, and actually, I don't need this. I don't need this one. This is an error because I can simply do this. Okay. Then I will check that everything is correct. Half doesn't need to make any check on x to understand if it is even or odd, because I have the condition in the fast mult procedure. Fastmalt takes two arguments, A and B. As usual, I have the stopping condition when B reaches 0, and then we have a conditional procedure. If B is even, then the procedure called is double of fast malt of A and half B. If B is odd, so the other case, the else case in this conditional statement, I simply call the same procedure as before. As you can see, instead of the star, here I have fast malt, but fast malt is applied to A and B minus 1. And I checked, and everything works fine. Let's see, terminal. Chapter 1, bracket x 1.7 17. Yes, looks like it works. As you can see, in the case half of 5, the value returned by the procedure is 5 divided by 2. Okay, this was a very easy one. So I will. I do it now. I commit and push to my GitHub. So exercises 1.11, 1.15, 1.17. Git push, and we are done. Okay, see you in the next video. Bye bye.